Ladies and gentlemen, hello. This is Philip from ab9il.net and the YouTube Mach 7 Radio Intercepts channel. This is the second of two videos on the subject of recording from WebSDR and OpenWebRX interfaces. Before we go into the details of recording weak and noisy signals, let's review a few of the main points from the first video, recording strong signals under ideal conditions. Waterfall range. For strong signals, you can reduce the waterfall range. On OpenWebRX sites, it's an easy thing to do. You can set the lower end of the range to about minus 120 dB and set the top of the range to about minus 30. That will cause the background noise to appear relatively dark, and it will give you more coloring detail for higher amplitude signals, such as voice peaks. Agc threshold. The Agc threshold should be reduced to keep the background noise at a minimum. Set it to about minus 80 to minus 60 dB for very strong signals. If the signals are not extremely strong, then maybe minus 85 to minus 90 dB will work. Agc Hang Time. Prevent noise pumping in between syllables of a single sideband transmission or fast CW. And to prevent surges of noise whenever a carrier is dropped or a person stops speaking on sideband, I recommend the longest possible hang time. For OpenWebRX, set it to about 5,000 milliseconds. Agc Slope. For digital signals and constant carrier signals like AM or FM, the slope setting does not have much effect. If you're monitoring single sideband signals, you'll have a more natural sounding recording if you set the Agc slope to about minus 2 dB. Filter passband. Under ideal conditions, you can run with wider passbands. AM signals sound very nice with the passband between 5 and 7 kilohertz wide. When you're listening to a single sideband signal, under ideal conditions, 3 kilohertz is enough for most situations. Most transmitters won't go beyond 3 kilohertz anyway, and you can see it on the waterfall. If you're using the sideband mode on your receiver to copy an AM signal, well, you can extend your passband out to 4, 5, or 6 kilohertz, and things will sound very nice. Audio levels. Audio levels should be moderate but not too strong. Aim for a target of about minus 10 to minus 5 dB. RF bit depth and sampling rate. When you have a choice, use as high a sampling rate as possible and as high a bit depth as possible. Audio or baseband bit depth and sampling rate. Use as high a bit depth and as high a sampling rate as possible. At least 16 bits, 44,100 samples per second for audio at CD quality, 48,000 samples per second for video recording. If it is possible, go for 24 bits and 96,000 samples per second, and even higher. That's ideal for future editing and archiving purposes. Those were the main points of the first video. Now let's talk about recording weak and noisy signals. Now, how do we capture these signals? There are a number of ways. One way is to directly record the complex, that's the IQ or quadrature signal, before demodulation. Another method is to route the audio after demodulation to a PCM recorder application that's on the machine with the SDR, or you can use a separate audio recorder and use a patch cable. When you're recording weak signals, the default waterfall range as presented by OpenWebRX and WebSDR sites are fine. You don't really need to make changes unless you want to see more detail in the color contours. In that case, bring the bottom of the waterfall range up and bring down the top of the waterfall range. You make it more narrow, and then signal variations become more visible. As with the waterfall range, default AGC settings are generally okay. It's important to have a signal level that you can work with. Again, the target should be about -10 to -5 dB average. Default AGC settings are fine. You certainly want the AGC to remain engaged, and you want the signal to be at a moderate level. Let me remind you once more, the AGC should stay engaged when you're recording weak signals. That's a lesson from experience. There have been times in the past when I've been trying to make a recording of a weak signal with the AGC turned off or reduced in effectiveness, and a strong signal arrives on frequency and just about blasts my headphones off. It's very uncomfortable, and it makes for a really bad recording. When you're recording signals that are weak or subject to interference, you'll have to more actively manage the filter passband in the receiver. If there's interference from a station above or below the frequency that you're tuned to, the job is a bit easier. Simply adjust the filter passband to reduce interference and then leave the other side wide open for better fidelity. If you're unlucky and you have interfering stations above and below the frequency that you're tuned to, narrow the filter passband to try to protect the signal that you want and exclude the interference and noise from the other stations. Dsp Noise Reduction is a feature of most software-defined radios. I will say that less is more, however. Try not to overprocess the signal. If you don't need the noise reduction, don't use it. But if there's interference and noise, sometimes you do have to use it, and often it will help. Audio levels should be set to feed a moderate signal into the recorder, averaging at about -10 dB. That's good. If the signal is going higher than -5, it's too strong, and there is a possibility of overloading the recorder. Signals below -15 or -20 are simply low signals that will need adjustment during the editing process. Let's talk a bit more about bit depth and sampling rate. More is better. Sample at as high a sampling rate as possible. That applies to both audio and the RF part of an SDR. Bit depth sets the maximum theoretical dynamic range of a digital signal. 8 bits has a max range of 48 dB. 16 bits, 96 dB. A 24-bit signal will have a maximum theoretical range of 144 dB. 32 bits has a very high dynamic range of 192 dB. Those are theoretical ranges. It requires quite a bit of expertise and fine engineering to produce audio or RF equipment that will have that kind of range. Some of the better SDRs have the ability to oversample and decimate. What that means is that the SDR will operate at a sampling rate far, far higher than is necessary to capture a signal. And then the samples will be systematically removed. Magic math will be performed, and the end result is a signal of lower sampling rate, but higher bit depth and lower noise. SDR hardware comes with a variety of different bit depths. At the low end of the spectrum, we have the RTL SDR devices, which run at a bit depth of 8. 8 bits is rather marginal, but it does work. 12 to 16 bits is much better. It's more typical of the moderately priced SDRs. 16 to 24 bits is absolutely superb. There are some soft rock radios which are fashioned from quadrature mixers and audio interfaces. And I'm sure there are some high-end RF devices designed from the bottom up as RF devices that run at 24 bits. As to audio bit depths, 16 bits is the minimum that you want for a recording or an archive. 24 bits should be the standard. 32 bits is ideal for doing DSP. It's not necessary for archiving and video CD production. We'll use 16 bits. There are some digital sound processing devices that will upsample the audio to 32 bits, do the processing, run all kinds of magic math on the signal, and then reduce the bit depth back to 16 bits for an output. Now, higher sampling rates and higher bit depth will produce larger files. It might be a factor depending on your hardware. If you can accommodate larger files, then certainly go for the higher sampling rates and the higher bit depths. If you already have recordings of weak or noisy radio signals, they can be cleaned up with digital signal processing. Generally, the higher bit depths and sampling rates will yield a cleaner product. The minimum sampling rate for a recording should be 44,100 or 48,000 samples per second. 96,000 samples per second is much better. For most HF voice and digital modes, above 96 kHz is overkill. In some cases, broad sections of the radio spectrum can be captured as complex IQ signals. For IQ spectrum recordings, sampling rates above 96 kHz are not overkill. Use as high a bit depth as possible. Let's talk a bit more in depth about IQ, or complex quadrature waveforms. One really nice aspect of these kinds of recordings is that DSP can be applied before demodulation. The recordings could be made from most SDR applications. Once the recording is made, MATLAB and GNU radio modules are available to work with the signals. Digital Signal Processing Package WDSP has leading-edge code for eliminating pulse and random kinds of noise. The processing can be applied before demodulation, and in the end, the demodulated signal is cleaner. For demodulated signals in the audio range, plugins created for sound studios and home editing of audio can be used. LADSPA, LV2, Python processes, and MATLAB modules are all usable. Now, the high bit depths and high sampling rates and heavy DSP algorithms are great if you have a modern system with lots of cores, a fast CPU, and possibly a graphics processor to help out with the number crunching. Bear in mind that you do not have to run a high-performance computer system or a high-performance studio to do the digital processing. The main issue is that the effective processing can take longer time. It's a matter of how long you want to wait for the end product to be available. After the recording has been cleaned up using digital signal processing, enjoy the improved recording. Remember, though, to save the original for future reference and for possible improvements in future DSP capability. At this point, we'll go online, tune in a few noisy signals, and work with the DSP that is available from the SDR sites themselves. We'll see how effective the noise reduction is on the WebSDR, and we'll do a similar test and get some experience on the OpenWebRX sites. We're currently using the WebSDR at the University of Twente. The frequency is 5505 upper sideband, and that frequency is occupied by Shannon Volmet. Signal is strong. Unmute the audio and have a listen.
Gothenburg Landvetter, Metroport, Gothenburg Landvetter at 0520 Zulu.
Before we turn on the noise reduction features, let's talk for just a moment about noise. There are two kinds of noise. One is random noise. Random noise has no discernible pattern of amplitude or phase. It's broadband in nature. It covers the lowest frequencies received all the way up through the top. It sounds like hiss. On the waterfall, it is the background that we see. In the old days, watching television, the noise was the snowy scene in the background. The human voice from Shannon is composed of many individual spectral components. Notice that around 300 to 400 hertz, we see the strongest lines in the spectrum. Those are the lower parts of the human voice. As we look through the middle of the passband and up towards 3 kilohertz, those components are not quite as strong, but they are there. The noise reduction feature of the WebSDR uses what's called a least means squares function. Least means squares is a method of finding the frequency that a carrier is on or that a voice spectral component is on. The software then creates bandpass filters around each individual component of speech, thereby filtering out the random noise in the background. There's actually another function called the descent gradient function, which is how it can randomly pick and poke around in the spectrum and find components and discern trends. So if the person is changing the pitch of their voice, or if we're listening to CW or something else that is more coherent and it's moving in frequency, the filters will actually track that signal. You can see that Shannon Volmet is not speaking in a perfect monotone. The pitch does go up and down slightly.
Forecast minimum temperature 3 on the 7th at 0600 Zulu. Forecast minimum temperature 3 on the 8th at 0500 Zulu.
This is a strong signal. The noise is not much of a factor. This is what we would call armchair copy. Let's try another frequency where the signal is not as strong and we'll have to deal with background noise. We are now tuned to frequency 3413. Shannon Volmet is considerably weaker on this frequency. The background noise is much more of a factor. The good news is that the background noise can be reduced with the noise reduction feature of the WebSDR. Noise reduction on. Notice that the random noise has dropped in magnitude. Unfortunately, we are experiencing some gerbling and swishing in the background. That's because the signal is so weak that the LMS function in the noise reduction having a hard time finding spectral components to craft filters around. It's making random estimates at anything that seems for a brief moment to be coherent. It gets even worse as Shannon Volmet fades into the noise. At that point, there's just nothing. And you can't make something out of nothing. To mitigate those negative effects, I'll go to manual mode and reduce the aggressiveness of the LMS function. When the noise reduction is acting in a less aggressive manner, we hear more background noise and less gerbling. For archiving and recording purposes, that might be a bit more preferable. Let's compare. Noise reduction off. Noise reduction on. There's not much difference right there. Let's increase the aggressiveness just a bit. Noise reduction off. Well, pick your poison. Do you want noise? Or do you want swishing sounds? Is there a happy medium? Perhaps there is a happy medium where there is just a slight amount of swishing and less noise. Noise reduction off. So there's an example of how the noise reduction works in the WebSDR. Let's go and find some AM signals and try the sync detector and work with the adjustable filters. The receiver is currently tuned to longwave, frequency 225 kHz. On that frequency, there is a weak signal from Poland. The mode is AM, and that signal is subject to adjacent channel interference, carriers, and plenty of random background noise. We're going to work with the filter pass bands, software noise reduction, and change the detector type, all in an attempt to make that signal pleasantly readable. First, we'll unmute the receiver. Listen to all of that noise and racket. Next, we'll bring in the upper filter skirt. That's better. Bring up the lower skirt as well. Receiving bandwidth is a bit narrow, but much less noisy. Now, engage the LMS filter. That improves things a bit. And the auto notch. The auto notch does such a nice job of taking out that carrier. And I'm going to widen the filter pass band a bit. We'll stay away from that adjacent channel above. We'll bring out some of these skirts. That's much more listenable. Last but not least, we'll switch from the envelope detector for AM to the synchronous detector. That essentially brings on a product detector and an oscillator which is phase locked to the incoming carrier. Now that is a very nicely readable signal. We are now tuned to frequency 339 kHz from a receive site located in Portsmouth, England. We're going to do a little work with the noise blanker on the KiwiSDR. It works great. I'm going to unmute the audio and you will hear a non-directional beacon giving its Morse identifier, and there's plenty of pulse noise on the frequency. Bravo India Alpha is the identifier, and the pulse type noise, the buzzing that you hear, is quite audible. I have set the noise blanker up for a gate of 300 microseconds and the threshold of 80%. That seems to work well for taking out this noise. Notice that it disappears when the noise blanker is engaged. Noise blanker off. Noise returns. Noise blanker on. There is other weaker pulse interference on the frequency. That's due to other sources which are emitting the pulses with a different amplitude, phase, and duration. An 80% threshold in 300 microseconds seems to take care of this pulse very well. Judging from the pitch of the buzzing, I would guess that it is from the power lines around there. Let's do a bit more and turn on the denoiser. This should attack the random noise on frequency. It is so aggressive, it's taken almost everything with it. Let's go to extra screen. Presets for the LMS filter. Sideband 1, which is pretty aggressive. There's plenty of gerbling in the background. Not much else to hear. Sideband number 2 is less aggressive. They actually hear a bit more noise and fewer digital artifacts with this mode on. Well, there's not much difference with either. I let the noise blanker off just out of curiosity. Waterfall display shows that the pulse noise is back. We are still not hearing it, thanks to the denoiser. Denoiser off. Noise blanker on. There are still some more changes we can make to improve reception. The filtered passband is pretty wide. Notice that the Morse identification is quite low in frequency. What is it, 800 Hertz or so? I have forgotten the specification for non-directional beacons in the UK. It's a lower pitch than is used in the US. But we can close in a bit. We'll take out some of the higher frequency noise, pulling in the bandpass filters. Lower and upper skirts closer in. That noise is reduced. That's one way. There is another way, which is to go to single sideband, pull in the filter pass bands, only allow the Morse identification through. Really want to pull weak non-directional beacons out of the noise. do this. It also works on VHF if you're listening to localizer or VOR transmitters. Try this with the denoiser. A nice steady tone as this identifier is very good to use with the denoiser. It can handle those tones very well, even better than it handles the human voice. Noiser off. Close the adjustment panel. Noise blanker off. Let's remind ourselves how much we don't like noise by going back to what we had earlier. I'm going to show you one of the most annoying things on shortwave broadcast radio. There are two AM stations just a few kilohertz apart, creating one loud, obnoxious jumble of noise and a very loud heterodyne sound. We are going to use the auto notch to take out the beat note. Unfortunately, we'll still have to deal with the modulation. One of them appears to be music, the other one appears to be voice. Let's unmute and see what we have. Listen to that ringing sound. Okay, let's fix it with the auto notch. And just like that, the beat note is gone. Remember, the denoiser and auto notch work in a similar manner. They both look for short intervals at the audio, and they look for things that are coherent, which is spectral components of a human voice or music, or perhaps a carrier wave. The denoiser will form filters around the components of speech, thereby suppressing background noise. The auto notch is a bit different. It looks for carrier waves and suppresses them and allows the speech to pass through the filter unhindered. This appears to be two Chinese stations close together in frequency. I doubt that it's inadvertent. One of them is probably Taiwanese and the other one from the People's Republic. That is what's most likely going on here. Or there's a broadcast from Radio Free Asia or a religious broadcast, and they're sitting on top of it to wipe out that signal and make sure it's not listenable in anywhere near the PRC. Oh, let's move on and find another signal to test the auto notch on. Audio and recorder on. 11. Lesson begins now. Here is one more dramatic example of the difference the noise blanker can make. I have found a station on 648 kilohertz in the UK, which is absolutely covered by pulse noise. I'm going to unmute so that you can hear it, and then turn on the noise blanker to reveal the broadcast station underneath the noise. There it is. Let's try the denoiser. Pull out some of the white noise. Does it work? Maybe. Turn the volume up a bit. Well, it's working. There's music in there. try sideband 2. Doesn't seem to help much. Sideband 1. Nope. Those signals are so noisy, the denoiser is attacking everything. The noise blanker makes quite a difference. Let's turn the noise blanker off. Notice that the signal is lost in the noise now. This is one of the best features of the KiwiSDR, a noise blanker that works. And believe it or not, there are even better noise blankers out there in software. Except they're on very expensive radios, the Flex series of radios and OpenHBSDR equipment, which uses the WDSP processing engine. But that's okay. This is pretty good, and I'm sure it will get better. Thank you for watching.